Experts have just unveiled the world's first graphene semiconductor. Now, if you're not familiar with graphene, let me tell you, it's the superhero of materials science. The joke used to be that graphene could do everything but leave the lab, but in the last few years, that joke's been shattered. We're about to take a deep dive into the world of graphene semiconductors, right here on the Tech Report. Let's get started. Unleashing the power of graphene transistors. In the realm of semiconductor technology, silicon has long been the reigning champion, powering our modern world since its inception in the 1950s. The ingenious manipulation of silicon into tiny switches, known as transistors, laid the foundation for the digital revolution, shaping everything from computers to smartphones to smart appliances. Over the decades, the relentless pursuit of progress saw us doubling the number of transistors in integrated circuits every 2 years, a phenomenon famously encapsulated in Moore's law. Yet, as our reliance on silicon transistors grew, so did the challenges. We found ourselves bumping against the limits of silicon's capabilities in terms of speed, heat generation, and miniaturization. But what if there was a way to make transistors not just better, but 10 times better? Enter graphene, a material poised to redefine the future of electronics. Formed from a single layer of carbon atoms arranged in a honeycomb lattice, graphene possesses extraordinary properties. It conducts electricity with unparalleled efficiency, thanks to its minimal resistance to electron flow. This remarkable conductivity, coupled with graphene's strength, lightness, and flexibility, earned it the moniker of a wonder material. Despite its potential, graphene faced a significant obstacle: scalability. Until about a decade ago, cost-effectively producing graphene proved challenging. However, advancements in manufacturing techniques such as chemical vapor deposition and liquid phase exfoliation transformed graphene from a laboratory curiosity into a viable commercial material. The breakthroughs didn't stop there. Researchers soon discovered ways to leverage graphene's unique properties in practical applications. One such innovation was the graphene charging bank, capable of charging a massive 10,000 mAh battery in just 30 minutes, 5 times faster than conventional lithium-ion batteries. But amidst the excitement surrounding graphene's versatility, a fundamental question lingered. Could graphene serve as the basis for transistors, the building blocks of modern electronics? While graphene's exceptional conductivity made it an attractive candidate, its inability to switch off posed a significant challenge. However, scientists devised a workaround known as bandgap engineering, enabling graphene to behave like a semiconductor, a crucial requirement for transistor functionality. In this arena, the concept of the bandgap holds significant importance, delineating the conductivity of various materials. In insulators, this band gap is relatively wide, meaning that it requires a considerable amount of energy for electrons to transition to the conduction band. Consequently, insulators do not conduct electricity well under normal conditions. Semiconductors, on the other hand, boast a narrower band gap, allowing electrons to transition to the conduction band with the application of external energy. This property enables semiconductors to conduct electricity under specific conditions, making them the backbone of modern electronics. Metals, with their effectively non-existent band gap, permit electrons to move freely throughout the material, facilitating high conductivity. Graphene, however, presents a unique conundrum. Despite its exceptional conductivity, surpassing even that of metals, graphene is not a metal. Its conductivity stems from its honeycomb lattice structure, which allows electrons to traverse the material with minimal resistance. This paradox intrigued scientists who sought to harness the benefits of graphene's conductivity while retaining the ability to control its conduction. Thus, began the quest for graphene transistors, with researchers embarking on a journey to engineer a band gap in graphene, effectively transforming it into a semiconductor. Since 2008, scientists have dedicated themselves to this pursuit, employing various band gap engineering techniques. However, despite their efforts, success remained elusive. The resulting transistors failed to meet performance expectations, struggling to exhibit the desired semiconductor behavior. Nevertheless, the quest continues, fueled by the tantalizing promise of graphene transistors, devices that could revolutionize electronics with their unparalleled speed, efficiency, and versatility. Revolutionizing semiconductor manufacturing and the potential of semiconducting graphene. The process involves heating silicon carbide in an argon-filled quartz tube, inducing the evaporation of silicon and leaving behind a carbon-rich surface that forms graphene. This method, cost-efficient with relatively inexpensive materials, yielded individual transistors that outperformed current silicon chips in speed. Additionally, researchers successfully produced larger, robust semiconductor wafers. This breakthrough opens doors to scalable production of graphene-based electronics, offering unprecedented speed and efficiency in semiconductor manufacturing. Researchers have successfully transformed graphene into a semiconductor, a feat previously thought unattainable due to graphene's inherent non-semiconducting nature. By introducing a band gap to graphene, the team from Georgia Tech has unlocked a wealth of possibilities for this remarkable material in the field of microelectronics. This achievement not only expands the applications of graphene, but also paves the way for more efficient and advanced electronic devices. Unlocking better computers with graphene. Graphene holds the promise of revolutionizing computing as we know it. Not only does it enable the creation of smaller, faster, and more energy-efficient devices with reduced heat dissipation, but it also taps into electron properties inaccessible in silicon. This paradigm shift in electronics opens doors to unprecedented possibilities. The recently developed graphene semiconductor boasts remarkably high electron mobility, crucial for high-frequency terahertz range electronics. Compared to today's chips operating in the gigahertz range, higher electron mobility translates to faster transistor switching, enhancing the speed and efficiency of electronic devices exponentially. Imagine laptops and phones lasting for days on end while performing tasks 5 times faster. Moreover, the manufacturing method behind this breakthrough is both simple and cost-effective. Utilizing standard equipment and relatively inexpensive materials, it aligns seamlessly with conventional chip fabrication processes. This compatibility ensures scalability and economic feasibility for widespread adoption in the semiconductor industry, a rarity in research breakthroughs of this magnitude. Unlocking the potential of graphene in quantum computing. The breakthrough in creating a high-mobility graphene semiconductor not only holds promise for traditional electronics, but also opens doors to groundbreaking advancements in quantum computing. Unlike silicon, graphene exhibits pronounced quantum mechanical wave properties at low temperatures, offering a fertile ground for the development of new quantum devices and computing methods. This represents a significant paradigm shift from conventional silicon-based electronics. However, despite its immense potential, there's a caveat to consider. The band gap of the graphene semiconductor, at 0.6 electron volts, is smaller than the typical 1.1 electron volts found in silicon. While advantageous for certain applications like solar panels, this smaller band gap poses challenges for CPUs, potentially leading to current leakage and increased power consumption. Nonetheless, with continued refinement, this limitation is expected to be overcome, paving the way for unprecedented advancements in computing. Thanks for tuning in to the Tech Report. Until next time, keep dreaming, keep exploring, and keep pushing the boundaries of what's possible. See you soon!